In this video, we want to talk about one-dimensional kinematics and graphs. And if you look at the graph that we have, we're going to say there are three sets of graphs here. The first column of graphs, this whole column here, they're going to be position graphs. So this is going to be position. And what that means is that on our y-axis, all of our y-axes here are going to be the position or the displacement. Our second column of graphs, they're all going to be velocity graphs. And for those, that means our y value is going to be the velocity. And our third column of graphs is going to be the acceleration graphs. Acceleration, which again means that our acceleration is going to go on each of those axes. And then what's on the x-axis is going to be time for all of them. T, 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 time, time, and time. Now, whenever we look at these across the rows, these are really three sets of graphs. So I would look at this top row together, the position, the velocity, and the acceleration graph. And what I would say is for this row of graphs, this row is going to be constant position. So a constant position might be an object is just sitting there. It's not moving. It's not going anywhere. So you are sitting at a stoplight. So your position is staying constant. You're not moving from the stoplight. If you're not moving, remember that velocity is really the change in position over the change in time, which means if you're not changing your position over time, then your velocity has got to be zero. And again, remember by definition that acceleration is really the change in velocity over the change in time. And if you're not changing your velocity here, then your acceleration has to also be zero. So remember that that is really separate. That's its own set of graphs. Now, when we go to the next part, we're going to say that this is going to be a constant velocity. So an object is moving at a constant velocity. Maybe you are heading down I-65 going 70 miles an hour. Well, every second you are still going 70 miles an hour, that velocity is staying constant. Is your velocity changing? The answer to that is no, it's staying constant, which means the acceleration has to be zero. Now, if you're going 70 miles per hour, every hour you're going to go another 70 miles, which means your distance is going to increase linearly. And so you end up with a graph that looks something like that. That's your second set of graphs. Now, your third set of graphs would be if this was constant position, constant velocity, then the last set of graphs is going to be constant acceleration. And you can sort of notice the trend on this, that this constant value is coming down the diagonal. Isn't my acceleration going to be what's constant? Maybe this is I'm dropping a water balloon from off of the football bleachers to try and hit someone. Well, that acceleration of gravity, that negative 9.8 meters per second squared, is constant because that's what the Earth's pull is, the Earth's acceleration of gravity on the objects around it at the surface of the Earth. So then that means that every second, that water balloon is going to get 10 meters per second faster. So at the first second, it's going to be 10 meters per second. And the second, it's going to be going 20 meters per second. At the third second, it's going to be going 30 meters per second. So you get the idea. Now, if it's getting faster, then doesn't that mean that every second it's going to cover more and more and more distance? And that's where you end up with an exponential curve for your position graph. So that gives you three sets of graphs that tie into the different parts of the position, velocity, and acceleration, and the motion that an object may have. Now, let's take this one step further and talk a little bit beyond that and say, hey, when we look at these graphs, there are a couple different things that we can talk about. Like, hey, isn't this a line? So couldn't we say y equals mx plus b to describe that line? Well, isn't the y-axis the position? And isn't the x-axis the time? And won't the y-intercept be the initial position that you have? And how do we find the slope of this line? Well, isn't slope the y value over the x value, which in this case is your position over your time? Well, what is position over time? Yeah, didn't we just say that up here, that the position over time is the velocity? And so you'll notice that we end up with this kinematic equation, x equals vt, for objects that have a constant velocity. Distance equals rate times time. You may have heard it. So we can do the same thing down here with the velocity equation. We could say y equals mx plus b. Well, the y value is the velocity. The x value is the time. To find the slope, we're going to have the y over the x value, which is going to give us the velocity divided by time. And again, notice that that slope tells us the graph to the right. It tells us acceleration. So we can put that as our acceleration. And then if we have our y-intercept, that's going to be the initial velocity. And notice that that's where we end up with this second kinematic equation, Vf equals Vi plus At. We can also look at this guy and say, hey, when we talk about parabolas, don't they have a certain equation that's going to be y equals ax squared plus bx plus c? And the y value is our position. The x's are our times. And are you starting to see that this equation mirrors this equation, where that a is 1/2 of the acceleration, the b is really the initial velocity, and the c is going to be the initial position or the initial constant from there. So that gives you just a general idea. Now, if we were to tie this one step further, we could say, hey, these slopes really tell us the graph to the right. So slope to the right. And then there's one more thing we could look at, and that would be areas. So if y divided by x is something, then couldn't y times x be something? And that would be maybe if I look at this graph and I say, hey, if I take this graph and I say the y times the x, well, isn't this the shape of a rectangle? And wouldn't y times x really be the area that I see under that rectangle? So if I take y times x, my y-axis is the velocity, my x-axis is the time. Well, what is velocity times time? Yeah, if the slope goes to the right, then the multiplying or the area goes to the left. That's really equal to your position. And we can do the same thing down here where we take this and say, hey, if I take the y-axis A times the x-axis t, what is that? That area is going to give me the velocity to the left. So if the slope goes to the right, the area goes to the left. And then to tie this in a little bit to calculus, your slope is nothing more than a derivative or a gradient, is another way to say it, and your area is nothing more than an integral. So real basic idea, the slope gives you the derivative and the area gives the integral, and that gives you sort of the idea behind all these graphs and the kinematics that we're studying and sort of where those equations came from based off of Newton and some of the other physicists who studied this.